All right, welcome back to another episode of Science with Surback. Today we move a little bit further into our solutions unit and we start talking about colligative properties. Now, before we get into these notes, there's a couple of objectives that I would like you to be able to meet by the end of this video. Objective number 1 is to determine the concentration and molar mass of a non-volatile, non-electrolyte from its effect on the colligative properties of a solution. Objective number 2, explain the difference between the magnitude of changes in colligative properties caused by electrolytes compared to those caused by non-electrolytes. And objective number 3, describe the effects of a solute concentration on the vapor pressure, boiling point, freezing point, and osmotic pressure of a solution, and be able to calculate any of those properties described above given the appropriate concentration data. So we start out here with colligative properties, and colligative properties are defined as properties that depend on the number of solute particles. So a couple of key things here in this real simple definition of colligative properties. Number 1, this business here, this is about the solute, okay? This is going to be really important to identify the solute versus the solvent in our example problems. And the other thing here that I am going to write down is this. The colligative properties itself is not dependent upon the identity of that solute particle. Now, another important thing here to remember with colligative properties is that we have to worry about if something or if a solute is a ionic substance or a covalent substance. And so you may be wondering, okay, well, why do I need to check to see if a substance is ionic or covalent? You said, hey, the identity doesn't matter. Well, if we have an ionic substance, so we'll go with an example here, an ionic substance, we'll say sodium chloride, so NaCl, all right? We dissolve NaCl and we make a solution of salt water. Remember what happens here is this. When this gets dissolved in water, we have things, unique things that happen. We get sodium ions, which split apart from your chloride ions. And now what we have, and I would probably write this down if I were you, we've gone from one solid substance to now 2 ions in solution. Whereas something like a sugar, something that's covalently bonded, when it gets dissolved in water, so let's say C6H12O6, just as an example, solid sugar here. When it gets dissolved in water, all we're going to do is we are just going to have that aqueous solution of sugar water form. And what I mean by this is that, hey, that C6H12O6 is not going to break apart in additional pieces. It is just going to be completely surrounded by those water molecules, okay? So it's really important here to remember, if I have an ionic substance, it's going to break apart into 2 different ions. Thus, that will increase the number of solute particles in our solution. But on the other hand, if I have something that is covalently bonded, when it gets dissolved in water or another solvent, it is going to stay as one substance. It's not going to be broken down into 2 different parts. And so this would not affect the number of solute particles here. So something, as we go through some problems here, we will have to keep that in mind. Now, let's move down to the 4 colligative properties here. And these are properties that we'll go over in more detail. The first colligative property is vapor pressure lowering. The second colligative property is boiling point elevation. The third colligative property is freezing point depression. And the fourth colligative property is osmotic pressure. All right, so what we're going to do now is we're going to go into details of each of these 4 colligative properties. So we start out here with the first one that was listed, and that is vapor pressure lowering. Now, vapor pressure lowering occurs when a solution consists of a volatile liquid, solvent, and a non-volatile solute. And so this term volatile and non-volatile, what this means, if something is volatile, this liquid is going to evaporate easily. So you have a solvent that evaporates easily and a solute that does not easily evaporate. And they mix together and they form this solution to cause this vapor pressure lowering. Now, with vapor pressure lowering, what we can do is we can apply a law to describe what happens here. And that law is called Raoult's law. And what Raoult's law is defined as is a way to quantify the extent to which a non-volatile solute lowers the vapor pressure of the solvent. Now, that's great that we have a definition, but we can also apply a formula to Raoult's law. So that formula of Raoult's law is going to be the vapor pressure of the entire solution is going to be equal to the mole fraction of the solvent times the original vapor pressure of the solvent. Ultimately, because we had a solute, the mole fraction will be lower than 1 and ultimately lower the vapor pressure of the entire solution. So again, just to go over these particular terms in this formula, the P of the solution is the vapor pressure of the solution. The X of the solvent is the mole fraction of the solvent. And then the pressure of the solvent is the original vapor pressure of that particular solvent, or we sometimes call that the vapor pressure of the pure solvent. Okay, so let's go ahead and try Raoult's law, the actual formula here, in a particular example. Okay, so we move over here to our example, and we have glycerin, which I give the formula here. Glycerin is a volatile non-electrolyte with a density of 1.26 grams per milliliters at 25 degrees Celsius. We want to calculate the vapor pressure at 25 degrees Celsius if 50.0 milliliters of glycerin is added to 500.0 milliliters of water. The vapor pressure of water at 25 degrees Celsius is 23.8 torr. And the density of water is 1 gram per milliliter. Now, the first thing that we need to get to is our mass of both glycerin and water. And it's not explicitly given, but we can do a little bit of work to get to that point. So I'm going to start here with glycerin. Okay, glycerin, we are given the density of glycerin, and that density is 1.26 grams per milliliter. So just to remind you what I'm doing here is I'm going to find or utilize what I know about glycerin, which I know its density, so 1.26 grams per milliliter, equals our mass, which nowhere on here does it say anything about mass, so that's going to be our variable, and it's going to be divided by our volume, which it says in our problem we have 50.0 milliliters of glycerin. So we put down 50.0 milliliters of glycerin, and what we're going to do here is we're going to cross multiply these numbers. So all I'm going to do in my calculator is I'm going to take 1.26 and multiply it by 50. Now, when I do that, I get the number value 63, and that 63 is the number of grams of glycerin. And I'm going to go ahead and I'm going to put the formula for glycerin of C3 H8O3. Now, I need in my mole fraction not grams of glycerin, but I need moles of glycerin. And to help you out, to save some time, the molar mass of glycerin is 92.09 grams per mole. Okay, so when I set up my conversion here, I have 92.09 grams of glycerin for every 1 mole of glycerin. So 1 mole goes on top. And so what I'm going to do in my calculator is I'm going to take 63 divided by 92.09. So 63 divided by 92.09. I press enter, and I can round to 3 significant digits. So I'm going to round to 0.684 moles of glycerin. Now, that is just my solute. I need to do the same exact thing for water, my solvent. So I go over here, I start out with water, and again, I am not given the number of grams of water, I'm not given the number of moles, so I have to do the same exact thing. I have to have my D for density equals mass divided by volume, and the density of water at 25 degrees Celsius is given to me at 1.00 grams per milliliter, and it's equal to our mass, which again, it does not give our mass of water, but it does give our volume of water to be 500.0 milliliters. So I put down 500.0 ml. Now, hopefully you can see this, but if you can't, 1 times 500, 1.00 times 500.0 is going to be 500. Okay, so what that means is that we have 500 grams of H2O. Now that doesn't help us out with our mole fraction, so we need to convert this. And just a reminder here, for water, I'm going to draw an arrow. For water, the molar mass is 18.02 grams per mole. So again, we put 18.02 grams of H2O on bottom to every 1 mole of H2O. All right, so in my calculator, what I'm going to do here is take 500 divided by 18.02, and I get 27.7 after I round it to 3 sig figs. So again, 27.7 moles of H2O. All right, so now this really helps in what we're about to do. We're going to plug all of these values, and there are only a few actually, to plug back into our Raoult's law. So I know space is limited here, but remember, Raoult's law says, hey, the vapor pressure of that solution is equal to the mole fraction of the solvent multiplied by the vapor pressure of the pure solvent. So we're just going to go through, we're going to fill in what we know and what we don't know and solve for this. So our pressure of the solution is something that we don't know. We're trying to find that. The mole fraction is going to have to be solved for the solvent. Now remember, the solvent is the item or the substance in the greatest amount, so it happens to be water. So what we do, we put the number of moles of water, so 27.7 moles, divide that by the total moles, which is 0.684 moles plus the moles of water, which is 27.7 moles, and we go ahead, we press enter, or we put it into our calculator, so 27.7 divided by 0.684 plus 27.7, and we press enter. Now, we've been using 3 significant digits, so we'll continue to do that. We have a mole fraction here of water, our solvent, of 0.976. Okay, so 0.976. And again, that is unitless. Now, the pressure of the pure solvent, which once again, it's water. The pressure of the pure solvent is 23.8 torr. And again, 23.8 torr is a value that can be found in usually an appendix, and that's where I found this value here. But torr is just a unit of pressure. Doesn't matter what unit of pressure that you use, as long as it is 1 unit of pressure. So I know space is kind of limited here, so I'm going to squeeze this in. But the pressure of the entire solution, or the vapor pressure, is equal to 0.976 times the original vapor pressure of that pure solvent, which is 23.8 torr. Okay, so all I need to do to calculate this out in my calculator is put 0.976 times 23.8. Okay, I get a value, again, 3 significant digits, because that's what I've been doing this entire time. I get a value of 23.2, and that unit would be consistent of that unit of pressure. So 23.2 torr is the vapor pressure of our solution. So you can see here, remember this is vapor pressure lowering, that's what Raoult's law explains, that by having a solution, the vapor pressure of the solution itself is lower. And that's because we added a non-volatile, non-electrolyte, which was in this case glycerin, and that's how it lowers our particular vapor pressure. All right, so now what we need to talk about here is kind of an extension of what we have here, and it kind of helps explain some of the things or assumptions that we make, and that is with an ideal solution. Now, an ideal solution is just defined as a solution that obeys Raoult's law and implies uniformity in the interaction between the solvent and the solute. Now, to be an ideal solution, there's a few conditions that must be met. The first condition is that the solute concentration has to be low. The second condition is that the solute and solvent have similarly sized molecules. And the third condition that has to be met is that the solute and solvent have similar types of intermolecular attractions. All right, so I know we haven't talked a whole lot about intermolecular attractions, but basically what these conditions are saying is nothing can be crazy out of line. So we can't really have differences in terms of intermolecular attractions in these particles, because the more intermolecular attractions we have, the more it's going to affect how the solution behaves, and the more it affects how a solution behaves, the less it can obey Raoult's law. Raoult's law is really nice when we meet these conditions, and it can help predict what the vapor pressure of the solution is. But when we start getting a little bit crazy, especially with the intermolecular attractions, they start pushing and pulling on one another between solute and solvent, it's going to affect how that solution behaves. So just know, hey, we have to meet these conditions, and if they're not necessarily met, or if you have crazy intermolecular attractions, really strong intermolecular attractions, you're going to affect how that solution behaves. Now, on a statement here, on an end statement here for an ideal solution, a non-ideal solutions occur when solvent-solvent and solute-solute intermolecular forces are much greater or weaker than solute-solvent intermolecular forces. So again, the easiest way to think about this statement here is that if these attractions are way off from each other, the solution itself is not going to obey that idealness that we just talked about here. The more you deviate from an ideal solution, the less that Raoult's law can be applied. All right, so let's go ahead. Let's move on to our second of 4 colligative properties. And that second of 4 colligative properties is known as the boiling point elevation. And now the boiling point elevation occurs because a solution has a lower vapor pressure than the pure solvent. And so what this does, it allows the boiling point of the solution to be higher than the pure solvent. And so again, I just want to point out too, because we lower the vapor pressure, again, kind of in a continuation of what we just talked about, we affect the boiling point. We actually raise the boiling point of that particular solution. So you produce a solution, it's going to have a higher boiling point than the pure solvent. Now, to help us out here, the boiling point elevation has a formula to go along with this. And so that formula here is known as delta TB, which is the change in boiling point, is equal to KB, which is the boiling point constant, times little m, which remember from solution concentration is molality. So again, to go over each of these, I want to be clear, but our delta TB is the change in boiling point temperature. Now, this is the change. So if we want to find out the actual boiling point, we're going to need to add this particular number to the original boiling point. Now, our next thing here, KB, is known as the Molar boiling point elevation constant. And then the m, remember little m, is going to be the molality of the entire solution. All right, now a really, really important point here. I made it at the very beginning of these notes, but this point here is this, or as follows. An electrolyte solute in the solution will impact the colligative molality of the solute. So again, our example here, if we have solid sodium chloride dissolved in water, I'll add water this time, it breaks down into sodium Na plus ions, and it breaks down into chloride ions. And then of course we would have H2O still in that particular solution. The point I'm trying to make here is, let's say for example we have a 1 mol concentration of NaCl. Because Na and Cl break into their respective ions, if we had 1 mol of NaCl, we'd actually have 2 mol because of the nature of the solution. And we'll see that in a couple examples that we will do. Now what I want to shift gears, before I do an example, a very similar type of concept here to go along with boiling point elevation, and that is the concept of freezing point depression. So freezing point depression is going to occur because a solution has a lower triple point than the pure solvent. Now we haven't really talked about phase diagrams at all, but the triple point, just so you know, the triple point is where all 3 states of matter, solid, liquid, and gas, simultaneously coexist. So we're lowering that point down, and what this does, it allows the freezing point of the solution to be lower than the pure solvent. Now to help us out here with the freezing point depression, there is also a formula that is associated with this term. And this formula looks really similar to what we saw with boiling point elevation. But this time we have delta TF, which stands for change in freezing point temperature, equals KF, which is our molar freezing point constant, times our molality of our solution. And just to be clear again, going over this, writing it down, our delta TF is known as the change in freezing point temperature. Our KF is our molal freezing point depression constant. And then our M is the molality of the solution. Okay, so let's put our knowledge of the boiling point elevation and freezing point depression formula to the test here. Okay, so what we have here is automotive antifreeze, also known in the chemistry world as ethylene glycol. Now, ethylene glycol is a non-volatile, non-electrolyte, and we want to calculate the boiling point and freezing point of a 25% by mass solution of ethylene glycol. And it is dissolved in water. Water is very important in this particular problem. The other thing that I want to mention is this. In the problem, it says, hey, this is a non-volatile and, more importantly, non-electrolyte. So ethylene glycol, when it's dissolved in water, is not going to break into multiple pieces. So for this problem here, we don't have to worry about multiplying the molals or the molality in our solution. We can just go straight forward. If this was an electrolyte or an ionic compound, this would be broken down into several parts, which would ultimately affect molality. We do not need to worry about that in this case. So now let's get down to 25% by mass of ethylene glycol and water. So again, whenever we have percentage, just make your life easy and say, out to the side here, we have 100 grams of solution. And if it's 25% by mass is ethylene glycol, that means that 25 grams of ethylene glycol, which is our solute, is going to be subtracted out of our particular solution, okay? So again, I told you that's going to be subtracted out because it's 25% by mass. This means that the remaining part of the solution is 75 grams of our solvent, which is water, okay? So this is really nice here because it breaks us down of what we have for our solvent and our solute. 25 grams of ethylene glycol is our amount or substance of the solute. 75 grams is our amount of our solvent or water in this case. Now what we want to do before we even get using the change of boiling point elevation and the change of freezing point depression, I want to calculate the molality, because remember, we're going to use molality in both the freezing point depression and the boiling point elevation. So just as a reminder, our little m is going to be equal to our moles of our solute divided by our kilograms of our solvent. Again, our M for our molality, we don't know. If we knew it, we wouldn't be going through all this trouble. Our moles of our solute, okay, our moles of our solute. Again, we don't have that given to us, but we just went through this scenario here where we have 25 grams of ethylene glycol. Okay, so we have 25 grams of ethylene glycol, and to help save some space, I'm just going to call ethylene glycol EG. So ethylene glycol can save some space here. And to save some time here, ethylene glycol has a molar mass of 62.07 grams per mole. All right, so 62.07 grams to every 1 mole. In our calculators, all we're going to do is take 25 divided by 62.07. So you have 25 divided by 62.07. We press enter, and rounding to 3 significant digits, we get a molality of 0.403. So 0.403 little m. And then our kilograms of our solvent. Once again, we just went through that process here to find that we have 75 grams of water. Well, that's not in kilograms. So remember, all we need to do to go from grams to kilogram is divide by 1,000. And so when we take 75 and we divide it by 1,000, so 75 divided by 1,000, we press enter. We get a number of kilograms of 0.075. So now all we need to do to plug this into our particular example here, our molality is going to be equal to our number of moles. And I need to make that clear. That's moles of our solute. So we have 0.403 moles divided by the kilograms of solvent, which is 0.075 kilograms of water. Now, we plug that into our calculator. So we have 0.403 divided by 0.075. We press enter. And again, rounding to 3 significant digits, we get 5.37. So our molality in this case becomes 5.37. Now that is a huge help for what we're about ready to do. I'm going to break this into 2 separate categories. The first category here is I'm going to talk about, hey, what is the new boiling point of my particular solution? And I'm going to go about halfway here, and I'm going to do the same thing, but I'm going to break it up to our freezing point. Okay? Now, our boiling point elevation formula is this. The change in our boiling point temperature is equal to our Kb times our M4 molality. Now, I'm going to go through these and we're going to talk about each and every one of these variables. And we start out here with the change of our boiling point. We don't know that. We're trying to solve it. If we knew it, we would just go ahead and utilize that number. Now, our Kb, I didn't really talk about here the constants, but our constants for this class are going to be given. So I have a chart which I will attach, but we look for the constant, the molal constant for your solvent. In this case, it is water, H2O. Again, we need Kb. So be very careful here. Go to Kb. Well, you see that Kb has a value of 0.51 degrees Celsius per m for molal. So we write down exactly what we see there of 0.51 degrees Celsius per m. So 0.51 degrees Celsius per m. Now our molality, our little m, we just spent the time calculating that, and we found our molality for this particular solution to be 5.37 m. Now, we go ahead, we plug these values back into our particular formula, so we get delta TB is equal to our boiling point elevation constant, 0.51 degrees Celsius per molal, times 5.37 m. So we go ahead, we calculate that, so we put 0.51 times 5.37. And because our constant here was given at 0.51, we're going to round to 2 significant digits, so this rounds to 2.7. Now, this is the change in the boiling point temperature. The problem says, hey, what are the new boiling points and freezing points of this particular solution? So to do this, we have to go one additional step. The first thing that we need to do is we need to look up what is the normal boiling point of the solvent? Which we said before, the solvent in this case is water. Well, look here. The normal boiling point of water is 100.0 degrees Celsius. So what I'm going to do is I'm going to write down 100.0 degrees Celsius. And because, think about this, boiling point elevation. Elevation means it's going to rise. Because it's going to rise, we're going to add that value of 2.7 to our particular formula. So we have 2.7 degrees Celsius. So ultimately, the new boiling point, or BP, of this particular solution is going to be 102.7 degrees Celsius. And that is going to be your new boiling point. And I'll put that down here, BP, for boiling point. Now, our freezing point, we're going to do a very similar thing. And remember, our freezing point formula is going to be delta TF equals our KF times our M for molal. Okay, so delta TF, again, if we knew that, we wouldn't be going through this trouble. So that is our question mark. Our KF, again, is a constant. And it's a constant for the solvent. We've already established that our solvent is water. And so our KF in this case is 1.86 degrees Celsius per molal. So we have 1.86 degrees Celsius per molal. And then our M, we spent the time to calculate it, to be 5.37 M. So we have 5.37 M, and we go ahead, we plug these values back into our formula. So we get our delta TF equals 1.86 degrees Celsius per molal times our 5.37 molal. Okay, so what we do here, we take 1.86 times 5.37, we press enter, and now we had 3 significant digits, so we can go ahead, we can use 3 significant digits, and so this would round to 9.99 degrees Celsius. Now, again, that's not our final answer, that's just the change of our freezing point. So our freezing point here is going to be this. We need to look up what is the normal freezing point for our solvent water, and we look it up here. We see here our normal freezing point of our pure solvent water is 0.0 degrees Celsius. So our normal freezing point is 0.0 degrees Celsius, and we subtract that. We subtract that because it's the freezing point depression. And so when we subtract that, we're going to subtract this value here. And so our new freezing point is going to be negative 9.99 degrees Celsius. Now, it's important to remember what solvent that you have, because that affects your constant, and then it also affects your normal freezing point and boiling point of that particular solvent. All right. So there's a lot on this page here, a lot we've smushed into one particular problem. Now what we can talk about is the fourth and final colligative property, and that colligative property is known as osmosis. So osmosis is defined as the net movement of a solvent from an area of low solute concentration to an area of high solute concentration. Now, this is a biological term, and it occurs, or osmosis occurs, in a system with a semi-permeable membrane. So to go along with osmosis, we need to talk about the term osmotic pressure. So osmotic pressure is defined as the pressure required to prevent osmosis. And this depends upon the solution concentration, and is also considered a colligative property. Now, osmotic pressure also has a formula. So the formula for osmotic pressure has this following symbol. All right, it looks like a pi symbol. is equal to the number of moles divided by the V for volume times your gas law constant at your current temperature. And this is also equivalent to your M for molarity equals to that ideal gas law constant times your temperature. And again, just to break this down here, the symbol that looks like a pi symbol is known as the osmotic pressure. Your N on top here is the number of moles. Your V is your volume of solution. Your R is your ideal gas constant. And then your T is the absolute temperature. Now, I don't have an example problem, but know that when a biology teacher or this term is brought up in biology, know that chemistry is going to affect those particular properties. And if you really wanted to calculate that osmotic pressure and see the flow of your solvent from area of a low solute to an area of high solute concentration, this would be the process to go about that. Okay, so now what we're going to do here, again, I don't have an example problem for osmosis, but I have a total inclusive property of our colligative properties. And we really need to think about what we have learned this far to be able to accomplish this particular problem. Okay, so we have a lot going on, and we have to piece together almost everything that we've learned up to this point about solutions. So we have a solution of an unknown, non-volatile, non-electrolyte. Does not break up, that's important. It was prepared by adding 0.250 grams of this unknown substance in 40.0 grams of carbon tetrachloride. The boiling point of the resultant solution was 0.357 degrees Celsius higher than the pure solvent. Ultimately, we want to calculate the molar mass of the solute. So, our end goal, we have to have a roadmap here. Our end goal is to figure out grams per mole. Well, as we look at this problem, we have a lot of information, a lot of numbers, and we need to sift through. We need to decipher, well, what is really important? Well, if we look here, 0.357 degrees Celsius higher, okay, that is giving us our boiling point elevation. How much higher did this particular solution, how much higher is that boiling point than the pure solvent? So we're given delta TB. And I'm going to start out this with delta TB equals our KB times our M4 molality. Now, our delta TB, and we're just going to list this here, our delta TB is equal to 0.357 degrees Celsius, so 0.357 degrees Celsius. And then our KB, you may be at a loss here, but look at this. Hey, we had the unknown solute dissolved in 40.0 grams of carbon tetrachloride. So CCl4, this becomes our solvent, and ultimately we can use that to solve or find our KB. And we're using KB because we are giving the boiling point elevation of this particular solution. So we find carbon tetrachloride, and it has a value of 5.02 degrees Celsius per molal. So our KB is 5.02 degrees Celsius per molal. Now our molality. It's really hard to calculate molality if we're only given the grams and no molar mass. We can't find moles. So what happens here in this case is our M, our molality, actually becomes our question mark. So what we need to do is plug these values back into our formula. So you would end up with 0.357 degrees Celsius equals our KB, which is 5.02 degrees Celsius per molal times our question mark, our molality, okay? And what we end up doing to solve for M, we just divide each side by 5.02 degrees Celsius per molal. And in our calculators, what we're going to do is this. We are going to take 0.357 degrees Celsius divided by 5.02 degrees Celsius per molal. So we have 0.357 divided by 5.02. We press enter. We're going to round to 3 significant digits. So our molality, our M, becomes 0.0711 moles per kilogram of solution. So molality equals 0.0711 moles per kilogram. We're still not at grams per mole. We're still not at that molar mass of this unknown compound. But we can get a little bit closer here with our molality. And so if we go to the second part of this problem here, we need to think about what molality stands for. Well, molality is moles of our solute divided by kilograms of our solvent. And we have just established that our molality is 0.0711 moles per kilogram. So 0.0711 moles per kilogram. Our moles of our solute, I'm just going to put moles, equals our question mark because we don't know what it is. And then our kilograms of solvent, I'm going to put this below here, our kilograms of our solvent is this. Remember I told you, hey, carbon tetrachloride is our solvent. We are given 40 grams of carbon tetrachloride, and we need to get it into our kilograms. So all we need to do here is we need to divide by 1,000. And that is for every 1 kilogram. Well, if we do that, that gets us a value of 0.040 kilograms. All right, I know things are kind of scattered everywhere here, but I'm going to put everything together. So our molality here is 0.0711 moles per kilogram equals our moles of our solute. Okay, we don't know what it is, divided by 0.040 kilograms. Okay, I'm going to cross multiply to find out our moles of our solute. So we have 0.0711 times 0.0440, and we press enter. Now, rounding to 3 significant digits, we get a value of 0.0028. So our moles of our solute, so moles solute equals 0.00284 moles. We're not quite done because we need the molar mass. So the molar mass in this particular case here is going to have to take the number of grams divided by the number of moles that we just calculated. Okay, and so I'm running out of room, I know that, but our molar mass, I'm going to squeeze it into the left here, our molar mass is going to take the number of grams of our unknown solute, so 0.25 grams per 0.00284 moles, okay? So our molar mass, when we plug this into our calculator, is going to be 0.250 divided by 0.00284. We press enter, rounding to 3 significant digits. Our molar mass of our unknown solute becomes 88.0 grams per mole. 88.0 grams per mole ultimately becomes our final answer. All right, I know I squeezed a lot in here, But remember, we use our molality formula to find our moles, and then we plug that back into our molar mass, grams per mole, to find our final answer of 88 grams per mole. All right, this has been quite the episode of Science with Surback. There's been a lot of information put into this episode. I hope you have enjoyed, and if you haven't already, make sure you subscribe.